Hello everyone, welcome to Brain Blitz Audios. Today, in this episode of NEET Preparation, we'll be looking at previous year questions of physics in medical entrance examinations in India. Today, we're dealing with the chapter Alternating Current. This is the 7th chapter in the grade 12 syllabus for physics in CBSE. This is a very important chapter for medical entrance exams, and a lot of questions are asked from this chapter over the years. Let's look at our first question for this episode, asked in AIMS 2011. An inductor coil of inductance L is cut into two equal parts, and both the parts are connected in parallel. The net inductance is L, L by 2, L by 4, 2L. These are the four options given. How do we solve this question? It is worth noting that the inductance of a coil is directly proportional to the length of the coil. So for instance, if we have a coil of length small l and an inductance of capital L, if we cut this coil into half, say two coils with length L by 2, then according to the relation, the inductance of both of these coils will be halved as well. So for each coil, the inductance will now be L by 2 if it's halved. So let's prove this statement by using this relation. So right now, we have the two parts of the same inductor connected in parallel to a potential difference source, and each of these have L by 2 as their inductance. So one of the inductance, since it's the half of the total inductor coil, so this will be L by 2, and the other part will also be L by 2. We need to find the equivalent inductance of this setup. So since both of these are connected in parallel, the formula here that we'll be using is 1 by L equivalent is equal to 1 by L1 plus 1 by L2. So here, let's use LCM. So it will become L1 plus L2 divided by L1 times L2 on the right-hand side. This is for the inverse of the equivalent inductance. Now what we do is we invert both sides. So therefore, L equivalent will be equal to L1 times L2 divided by L1 plus L2. In this formula, the values of L1 and L2 are equal. They're both equal to the half of the original inductor coil. So therefore, it'll be L by 2 times L by 2 divided by L by 2 plus L by 2, which results in the numerator as L squared divided by 4 and the denominator as 2L divided by 2. Therefore, L equivalent is now equal to L squared divided by 4 divided by 2L by 2. The 2's get cancelled, the L's get cancelled. So therefore, finally, we have the equivalent inductance as L divided by 4. This is the case when one inductor coil is cut into two equal parts and then they are connected in parallel. So the total inductance, the equivalent inductance, is L divided by 4, where capital L is the inductance of the original coil. If we look at our options, we find that option C is the correct option. And we calculated it by using the relation that the inductance of an inductor coil is directly proportional to the length of the coil itself. So if we cut a coil into two parts, then the inductance gets halved as well. Therefore, using that formula and by using the formula of 1 by L equivalent is equal to 1 by L1 plus 1 by L2, we found the net inductance to be L divided by 4. Let's look at our next question. You see a given circuit. This is an LCR series. This is an LCR circuit. However, it's not an LCR series circuit. As you can see that the resistance is connected in parallel to the LC part. And we have an AC source with V is equal to V naught times sine omega t. What we need to know is we need to find the current in the resistance R at resonance. So the condition of resonance, in this condition, the property of the circuit is that the inductive reactance is equal to the capacitive reactance. And for the formula of impedance, which is the opposition to the flow of current, the total formula is the whole under root of R squared plus XL minus XC, the whole square. So therefore, in this formula, if XL ever becomes equal to XC, then this component becomes 0. So therefore, the value of Z is equal to the resistance in the circuit of R. So we have a resistance R in the circuit. The impedance of the total AC circuit is equal to the resistance in R. And this is the condition for minimum resistance, minimum impedance. So there is minimum opposition to the flow of current since XL is equal to XC. And according to Ohm's law, I is equal to V by R. So therefore, if the impedance is decreased, the current automatically gets increased. So therefore, the right answer is option C, maximum but finite. The reason why it's not option D, infinite, because we have a set potential difference. The potential difference is set, so the current is also dependent on the potential difference given. So option C, maximum but finite, is the right answer. All the other options are incorrect. And we used it, and we found it out by applying the condition of resonance. So in applying the condition of resonance, XL equals XC, the formula of impedance can be shortened down to Z equals R. That gives us the condition for minimum impedance. So minimum impedance gives you maximum amount of current, which is finite because we have a set potential difference given. So therefore, option C, maximum but finite, is the right answer. Let's look at this question. An inductor L having a resistance R is connected to an alternating source of angular frequency omega. Find the quality factor Q of the inductance. So in order to find the quality factor of an LR circuit, we will divide the potential difference across an inductor by the potential difference across the resistor. So the quality factor Q is equal to potential drop across the inductor L divided by potential drop across R. If this was an RC circuit, then it will be potential drop across C divided by potential drop across R. So using this formula, the value of Q will be equal to the potential drop across inductor L is VL divided by the potential drop across the resistance R is VR. And over here, we apply Ohm's law once again. So in this situation, VL is equal to I times XL, where XL is inductive reactance. VR is equal to I times R, where capital R on the right-hand side stands for resistance. So therefore, Q, which is equal to VL by VR, now is equal to I times XL divided by I times R. The reason why we're doing that is because the current across the circuit here remains the same because it's a series circuit. So therefore, the current gets canceled. So therefore, we have XL divided by R as the value of the quality factor. Now, the formula for XL or inductive reactance is L omega. So therefore, the value of quality factor will be equal to L omega divided by R. If we compare the required answer to what we found out, then we can see that option D, omega L divided by R, is the right answer. Next question. In an AC circuit, the current flowing in inductance is I equals 5 sine 100t minus pi by 2 amperes, and the potential difference is V equals 200 sine 100t volts. The power consumption is equal to. So in this question, if you notice the values, I is equals 5 sine 100t minus pi by 2, while V is equal to 200 sine 100t. So over here, you can see that the current lags behind the voltage by a phase difference of pi by 2. So now we got the value of phi as pi by 2. Now this is all the value that you need to know. You don't need to take 5 or 200 or any of the other values, because the formula for power is VRMS dot IRMS dot cos phi. Power is the dot product of the potential difference and the current vectors. So cos phi is multiplied alongside VRMS and IRMS, their scalar values. So over here we got pi by 2 as the value of phi. So therefore, it'll be cos pi by 2. The value of cos pi by 2 in trigonometric ratios is 0. So therefore, the product on the right-hand side becomes eventually 0. So therefore, the power, the average power consumption here is equal to 0 watts. So therefore, because of the phase difference pi by 2, we get the value of power as 0 watts. This is true in the case of RC circuit as well, because over there, current leads voltage by pi by 2. So therefore, the phase difference is once again pi by 2. So therefore, since cos pi by 2 is 0, the power consumption in an RC circuit is also 0. The right answer is option D, 0. Now we come to our final question. This is found in AIMS 2013. For the circuit shown in the figure, the current through the inductor is 0.9 amperes, while the current through the condenser is 0.4 amperes. Condenser here refers to C, which is a capacitor. So IC is equal to 0.4 amps. IL is equal to 0.9 amps. Now, we're given 4 options. Current drawn from the generator, I, is equal to 1.13 amperes. Omega, which is the angular frequency, is equal to 1 by 1.5 into LC. I, the current, is equal to 0.5 amperes. I, the current drawn from generator, is equal to 0.6 amperes. If you look at this graph, this circuit diagram, you see that L and C are parallel. So therefore, for a given value of V is equal to V naught sine omega t, the current in the inductor, it is negative by a phase of pi by 2, and the current in the capacitor is positive by a phase pi by 2. So therefore, you can see that IC is anti-parallel to IL. Therefore, the total current I will be the sum of both these vectors. Basically, the current through the inductor is more here, and the current through the condenser is less. So therefore, the value of I is equal to IL minus IC. That is 0.9 minus 0.4, which gives you a total of 0.5 amperes as the right answer. The right answer here is option C. I is equal to 0.5 amperes. In this question, we're using the formula, not the formula, the idea of phase difference. For an inductor and the capacitor, there is a different kind of phase difference between the voltage applied and the current passing through. For an inductor, current lags behind the voltage, while for a capacitor, current leads in front of the voltage. So therefore, the direction of the currents passing through the inductor and the capacitor are anti-parallel. So therefore, the sum of both of these values will be 0.5 amperes, because one of them can be considered as negative. So here we considered IL as positive and IC as negative in order to get a positive value. So therefore 0.9 amperes minus 0.4 amperes gives you 0.5 amperes as the total current drawn from the AC source. And that concludes this webisode on NEET preparation. Today's chapter was alternating current, and we looked at some very important questions. To watch more of our videos on alternating current, don't forget to click the link in the description down below. And if you want to access more of our useful and interesting content, then don't forget to subscribe to our channel, which is Brain Blitz Audios. Until the next webisode, take care, stay safe, bye-bye for now.